brake resistor grid. See, it looks like an electric toaster in there.
Yeah.
I mean, an electric engine, like the Pennsylvania Railroad or in Europe, when a train's going down the backside of the Alps, they're putting energy into the wires, and you can actually theoretically power a train coming up the other side. Diesels don't have wires to put that energy that's generated into. You have to dissipate it as waste heat. And that's what the dynamic brake grid does. I've seen those things glow red. They put out a lot of heat, and when we go over, you're going to see how it's charred the paint on some of the other engines.
What is this grid at the front?
Okay, up here. Oh, by the way, take a look at the twin I-beam underframe of this. About twice the thickness of a normal diesel. Okay, right there, that's your locomotive breathing air. These engines were turbocharged. And the turbochargers right in there, they have a sealed air system, meaning they don't breathe like the old diesels did through oil filters behind a louver. The air gets centralized through the turbocharger. They have a centrifugal dust separator, and it's clean air going into the combustion chamber of the pistons. That also ups the power. If this engine wasn't turbocharged, you wouldn't get much over about 1,500 horsepower out of each motor. Instead, they got 3,300. Turbocharging was introduced by GM in 1959. Union Pacific had already been dabbling with it a couple of years before that, and was actually the catalyst of pushing GM off the cliff to build a bigger, more powerful engine. And that's when you begin to see the old Streamliner diesels be traded in, because two new ones did the work of 5 old ones. And even when fuel was only 20 cents a gallon, that was a huge savings in fuel and expense. So these are a few things about this engine where you can really explain dynamic brake and all this on this big monstrous locomotive. And I always tell people this steam engine is only a medium-sized steam engine. It is nowhere near the size of a Challenger or a big boy. It's a passenger engine. This was the world's largest diesel-electric freight locomotive. Now, we have 2 of the 3 world's largest here. The other one's the turbine. The only thing we don't have is the big boy. The turbine was bought to replace the big boy. These were bought to replace the turbines. And then conventional diesels grew to a point, because of fuel costs and efficiency of maintenance, where UP quit buying custom-made engines after the early 70s and went with standard off-the-shelf engines, and like all the other railroads, and created their own locomotive out of various units. Plus, railroads began to have run-through trains. Southern Pacific train would come in from Roseville, 120 cars of lettuce from California. The SB engines would pull right down into Riverdale Yard. They'd put one of these, and they'd put a regular UP engine on the front to activate the special UP cab signal system in Wyoming. And the train would go all the way to North Platte, Nebraska with SB engines and one UP engine. UP engines were all over Northern California on the SP. You could go to North Platte. In one day in 1970 in North Platte, you could see 15 railroads locomotives hanging out at the UP service rack there, because they had that many power pools with Southern and Seaboard and Missouri Pacific and Rock Island and Burlington. And those other railroads couldn't handle engines this big. Only UP could. So it became something of a dinosaur. They were cool to watch, but they cost more to maintain. They exhibited a lot of wear on the rail with these big D-type trucks with 4 axles on them. And once they started using common locomotives, you could use each other's engines and pay off what you owed the other railroad on a horsepower hour basis. I hope I'm not, this is a very complex subject. I'm trying to just get through it quick. So, any other questions? Yes.
Horsepower, would you run into some, do you have to make it heavier to get that to transfer?
Well, the engine got heavier because of its size, but General Motors came out with several advances in wheel slip control as these newer engines came out. They had to. Now, an SD45, like the SB engine over here, that is a 206-ton engine, 3,600 horsepower. The F7s, the old Streamliner diesels that they replaced, only weighed about 125 tons. Now, the SP, because it was a railroad with a lot of mountains, tractive effort was more important. They'd spin the wheels. They wanted to ballast the engines right up to the maximum. so they could get the most pulling power. So you could have an SD45 that only weighed 180 tons, but it would develop about 25,000 less pounds of tractive effort than an SP SD45 that was heavier. They'd actually weld plate steel inside the body, or they put concrete in them. Just depended on the engine. Scrapping them was a real bear, because you never knew what you were going to come across, but SP engines tend to have more metal in them. They were going upgrade or using dynamic brake. The basic motor is about this big. Remember, it has to fit between a 4-foot 8.5-inch gauge wheel set. On that wheel is a gear. That's your, I think they call it the bowl gear, the big gear. Then you got the pinion gear that comes out of the traction motor. You can't see it. There's 62 gear teeth on the bowl gear on the axle and 15 on the pinion gear. That means this engine has a top speed of 65 to 70 miles an hour. Now, when these engines were first built, these were freight engines, remember. You know what UP geared these for? 90. Doyle McCormick, you know, the engineer of the Freedom Train, he was also one of the engineers on the Golden Spike Limited. Yeah. He got one of these engines, the prototype, to 102 miles an hour on that special out in Wyoming. So, and these things ride really weird. It speaks. They have such a long wheelbase. They've got this weird float to them. And I've ridden in them, and it's very odd compared to other locomotives. But that's what the gear ratio is. The closer the two numbers are together, the lower the top speed, but the more pulling power. Amtrak engines geared for 103 have, I think, a 57-20 gear ratio. So now, does that make sense on this? And by the way, that's a brake cylinder. See the brakes down there. And the speedometer cable, let's see, it's not on this side of the engine, it's on the other side. This is your sand tube, putting the sand in front of the wheels. You know, now they use a radar wheel slip control. It shines a radar beam at the ground, compares it to the revolutions of the axle, and will close the throttle down automatically to compensate and match the two. Because when a diesel spins its wheels, it creates a flat spot in the rail. It peels a layer of steel off, looks like a metal carrot curl. You don't want to do that, because over time, trains pass by, they bang down on that spot, they induce metal fatigue, and the rail cracks at that spot. That's why diesels have this light right here. Right below the cab, there's a light on both sides. Because when you're out in the dark and your headlight's shining forward, you can start the train, it is vibrating, you don't know whether it's moving or not. That shone a light down at the ground so the engineer and the head brakeman could look down and know if they were moving, and if they weren't, they had to close the throttle down. Okay? Good physical condition. But the paint is starting to deteriorate. That engine was repainted by UP for us back in the 80s. Even sitting under cover, it's going to deteriorate over time. You see the rust starting to form, things like that. The engine is not in need of any dire work right yet. It looks pretty good where it is. But over time, if the museum is able to do this, you need to start establishing a repainting fund, because all of this equipment needs that. It's going to keep it from rusting out like the 223. Yep.